AP Chemistry Unit 6 is all about thermochemistry. It requires strong thinking skills and a good understanding of how chemical reactions work. Hi there, my name is Jeremy Krug, and this is the place for all things AP Chemistry. And in this video, we're going over the 10 things you've got to know from Unit 6. If you're new here, welcome aboard. Take a look around, check out my AP Chemistry playlists, that's where the action is, and make sure you subscribe. YouTube tells me that about 80% of you haven't subscribed yet, so what are you waiting for? It takes about 2 seconds, and it's an easy way to help out the channel. And if you're serious about getting that 5 on the AP exam, check out my ultimate review packet for AP Chemistry. It's got the full review videos for every unit, complete study guides, practice questions, and 2 full practice exams in the AP exam simulator. You can get a free sample today over at ultimatereviewpacket.com. Now, here are the 10 things you've got to know from Unit 6. Number 1. All physical and chemical processes take place as part of a system. The system includes only the particles that are changing over the course of that physical process or chemical reaction. In the lab, we make measurements of those chemical reactions or physical changes. For example, in AP Chemistry, we often use foam cups, or what we sometimes call a coffee cup calorimeter. The system is composed only of the particles of the material that's dissolving or reacting in that calorimeter. The surroundings include everything else in the universe. That includes the air in the room. That includes the foam cup, and the thermometer, and stirring rod are part of the surroundings. Even the water in the cup is part of the surroundings. Number 2. One way to determine if a physical or chemical process is exothermic or endothermic is to measure how the temperature of the surroundings change as the process takes place. Like we said earlier, the system is composed only of those particles that are actually reacting or participating in the change. And since it's essentially impossible to measure the energy change of those individual particles directly, we have to measure the temperature change of the surroundings. Now, since it's impossible to measure the temperature change of the entire universe, we insulate a small part of that universe, which in this picture is the foam coffee cup. We measure the temperature change of the water in that cup, and we assume that value is the temperature change for the surroundings. If the surroundings get colder, the process is endothermic. If the surroundings get warmer, the process is exothermic. For example, you may have held ice in your hand before, and you know that when ice melts, it makes your hand feel colder. Well, the ice is the system. Your hand is part of the surroundings. And since your hand is getting colder, that means the surroundings are getting colder. So we can safely say the melting of ice is an endothermic process. Number 3. In an exothermic process, the heat energy of the system decreases, releasing heat to the surroundings. In an endothermic process, the heat energy of the system increases, absorbing heat from the surroundings. In an exothermic process, the particles present at the beginning of the process have a higher enthalpy, and the particles at the end of the process have a lower enthalpy. Since enthalpy dropped, we can say that the sign for delta H, the change in enthalpy, is a negative number. This is what the reaction energy profile for an exothermic reaction would look like. The reactants start fairly high, and the products end up much lower, so there's a net loss of potential energy. And as you probably already know, if you put your hand next to an exothermic reaction, it's going to feel warm to the touch. On the other hand, in endothermic processes, the reactants begin with a lower enthalpy and the products end up with a higher enthalpy. So since enthalpy increases over the course of the process, the change in enthalpy for endothermic processes will always be a positive number. This is what the reaction energy profile looks like for an endothermic process. The reactants start out relatively low, and the products end up with a higher enthalpy. So there's a net gain of potential energy. And if you put your hand next to an endothermic process, it feels cold to the touch. Number 4, heat always flows from a warmer object toward a cooler object. Kinetic energy is transferred when faster particles collide with slower moving particles. The two objects reach thermal equilibrium when their temperatures are equal to each other. Let's say we have a bowl of hot soup. The soup has a fairly high temperature, while the air around the soup has a much cooler temperature. If we allow the soup to sit on the table without eating it, after several hours, the temperature of that soup decreases. It gets cold. How does this happen? Well, the soup gets colder because it transfers its heat to the surrounding air, which means that the surrounding air gets slightly warmer. The warmer particles from the hot soup collide with cooler particles from the air. And when faster, warmer particles collide with slower, cooler particles, kinetic energy is transferred. And eventually, after enough time, there's been enough energy transfer so that the soup particles have the same average kinetic energy as the particles in the air. The two temperatures are equal, and they've reached thermal equilibrium. Number 5. The equation Q equals mc delta T helps relate the transfer of heat for an object with the temperature change that object experiences. Let's take this example. A 26.5 gram sample of silver metal is allowed to absorb 477 joules of heat energy. This heat transfer causes the sample to rise in temperature from 21.2 degrees Celsius to 97.8 degrees Celsius. Based on this data, what is the specific heat capacity of silver metal? For calorimetry questions like these, we use the equation Q equals mc delta T, where Q represents the heat that's transferred in joules, m is the mass in grams, C is the specific heat capacity in joules per gram degree Celsius, and delta T is the change in temperature of the material. Well, the problem tells us that 477 joules are being transferred. That's our value for Q. M is the mass. That's 26.5 grams. We don't know the specific heat capacity, so C is the unknown. Delta T is the change in temperature. Since it goes from 21.2 degrees Celsius up to 97.8 degrees Celsius, that's a change of positive 76.6 degrees Celsius. We do some multiplication and division and find that the specific heat capacity is 0.235 joules per gram degree Celsius. Number 6. During a phase change, a material's temperature does not change. The potential energy required to change a substance from one phase to another can be used to calculate the energy change for the material. Let's say we have this problem. The enthalpy of fusion, or H fusion, for ethanoic acid, CH3COOH, is 11.7 kilojoules per mole. Determine the amount of energy in kilojoules required to melt a 50.0 gram sample of CH3COOH. Its molar mass is 60.05 grams per mole at its melting point. This is basically a dimensional analysis problem. We're starting with 50.0 grams of the substance, and the question asks us to determine the amount of energy in kilojoules to melt it. Step 1 is convert to moles, just like it is in pretty much any stoichiometry problem. So grams go on the bottom and moles go on top. The problem tells us that the molar mass for this substance is 60.05 grams. Grams cancel top and bottom. Step 2 is to convert to kilojoules. Well, moles have to go on the bottom, kilojoules go on top. And the problem tells us the enthalpy of fusion. That means it takes 11.7 kilojoules to melt 1 mole of this substance. We can cancel moles, top and bottom. And then we multiply and divide to find that it takes 9.74 kilojoules to carry out this process. Notice that if we take a solid and add heat to it, it causes the temperature to rise. But when it gets to the melting point, the temperature stops rising. The process of melting caused the particles to increase in potential energy, not kinetic energy. Once the substance is all melted, more added heat causes the liquid to rise in temperature as the average kinetic energy of the molecules rises once again. Once it gets to the boiling point, the temperature stops rising and the additional heat added increases the potential energy as it boils. Once the entire sample is converted to a gas, adding more heat causes the temperature to rise. This is called a heating curve, and it's a very common graphical expression of how heat and temperature are related to each other for a substance. Number 7. The enthalpy of reaction can be incorporated into a stoichiometry calculation to determine how much heat is absorbed or released when a certain quantity of substance is reacted. Let's take this reaction, where we have its delta H value, and it says we're asked to calculate the heat change produced when 5 grams of hydrogen gas are reacted with excess oxygen gas. We start with 5.00 grams of hydrogen, and the question asks us to calculate the heat change, which will be in kilojoules. So just like in any stoichiometry process, we always start by converting to moles. On the bottom, we put grams, so it'll cancel, and moles go on top. We can consult the periodic table and find that 1 mole of H2 has a mass of 2.016 grams. Grams cancel, top and bottom. In our second step, we convert to kilojoules. We put moles of hydrogen gas on the bottom and kilojoules on the top. According to the balanced equation and the delta H value, there are negative 572 kilojoules associated with 2 moles of H2. Remember, we incorporate the coefficients of the balanced equation. Moles cancel and hydrogen cancels. We do some multiplication and division to find the answer is negative 709 kilojoules. The negative sign implies that heat is being released. So we can say that 709 kilojoules of heat are released in this reaction. Number 8. Energy is released when chemical bonds are formed, and energy is absorbed when bonds are broken. The total delta H for a reaction is estimated by subtracting total enthalpy of bonds broken minus total enthalpy of bonds formed. Let's take the same chemical reaction we looked at earlier. We'll use this chart of bond enthalpies to estimate the value of delta H for this reaction. In hydrogen gas, the HH single bond has an enthalpy of 436 kilojoules per mole. Since we have 2 molecules of this, that means we have 2 bonds. So that gives us a total of 872 kilojoules for those bonds. The oxygen-oxygen double bond has an enthalpy of 498 kilojoules per mole. On the product side, we have 2 water molecules. Each oxygen-hydrogen single bond has an enthalpy of 463 kilojoules per mole. Since there are 2 water molecules and 2 bonds in each molecule, that means we're working with 4 bonds here. That's a total of 1,852 kilojoules. The sum of the bonds broken, those on the reactant side, is 1,370 kilojoules. And the sum of the bonds formed, those on the product side, is 1,852 kilojoules. Delta H equals bonds broken minus bonds formed. That's the left side minus the right side. So when we subtract, we find that the estimated delta H is negative 483 kilojoules per mole of reaction, which is reasonably close to the actual value. Number 9. The delta H for a reaction can be calculated more precisely by subtracting total enthalpy of formation of products minus the total enthalpy of formation of reactants. In this chemical reaction, we're looking at the combustion of methane in oxygen gas. For this process, we'll use the enthalpies of formation given to us in this table. CH4 has an enthalpy of formation of negative 74.9 kilojoules per mole. The value for oxygen gas is 0. Now, since there are 2 moles of that, we should multiply it by 2, which of course is still 0 kilojoules. The enthalpy of formation of carbon dioxide is negative 393.5 kilojoules per mole. And the value for water vapor is negative 241.8 kilojoules per mole. Since there are 2 moles, we multiply by 2 to get negative 483.6 kilojoules. The sum of the reactants is negative 74.9 kilojoules. The sum of the products is negative 877.1 kilojoules. And remember, delta H is found by taking the sum of the products minus the sum of the reactants. This is different from the last example. This time it's right side minus left side. When we subtract, we find that the delta H for this reaction is negative 802.2 kilojoules per mole of reaction. The negative sign tells us this is an exothermic process, which is what you'd expect from a combustion reaction. Number 10. If two equations can be added together to form a third equation, the delta H for the first two equations can also be added together to form the delta H for the third equation. Let's say we have these two balanced equations and their respective delta H values. Maybe we're asked to take this information to determine the delta H of this third equation. Well, we can see that these two equations can be added together, but only if we manipulate the reactions. If we flip equation number 1, we can change the sign on delta H. It was a negative value, now it's positive 1,640. At this point, the first two equations can be added together to give the third equation. We cancel the P4 molecules on both sides, and 3 oxygen molecules on both sides can cancel out. The first two equations do indeed add up to give us the third equation. That means we can add the two delta H values together and find that the delta H of the third equation is negative 1,300 kilojoules per mole of reaction. And that's it. Those are the 10 most important things you've got to know from Unit 6. Hey, if you're serious about upping your game for the AP exam, my Ultimate Exam Slayer for AP Chem has 60 AP-style multiple choice questions for Unit 6 and for each of the 9 units. That's way more than AP Classroom. You can get my Exam Slayer along with my Ultimate Review Packet, and you'll have everything you need to succeed in AP Chem. Go check it out over at ultimatereviewpacket.com. Hey, thanks for watching. Thanks even more for subscribing, and I'll see you soon.